let's see what we can do here. I'm going to share with you my desktop, and what I've basically done on the recommendation of the person that I know that just wrote the test. They indicated to me that the EQAO grade 9 math stuff was really a good benchmark that we could use to assess our level of readiness for the MPT. So the thinking was that I just pulled together a series of questions that have been used on previous EQAO tests, and that we kind of try them together, and that we go in the direction that we most feel we need to explore further. So I'm going to share that. Before we do, Lindy, there were some specific questions about the test itself, which I am not able to address, I think, as effectively as you are. Would that be included in that video that was shared from the young lady from?
Yes, so
yeah.
In a minute, I am going to put the link to the video up. Again, people should not worry about cutting and pasting these links because we will send them to you again. But there's a link with 11 great strategies on preparing. And this was a teacher candidate at York University who created it. And it really does have some very useful information about what the test looks like and how to prepare for it, including things that will help calm you, or even she has some guessing strategies, Leanne, which I really liked in case you run out of time and how to guess. So I've just put it in the chat, but I will be sending that out again. We did have Anka, who's joined us today, ask some questions, just some routine questions about, are you allowed to use paper and pen? And I figured lots of you would have those questions. Most of the questions that you will have, you can find answers to on the MPT website. So if you don't know where that is, it is on the EQAO site. You just go to EQAO, you find the assessment, and it takes you into the MPT site. I will provide that as well, but I'm guessing most of you have that because you've had to have that to register. But just to say, you are allowed to use paper and pen. Anka also asked, are you allowed to consult the growing success document during the test? And the answer to that is no, you're not allowed to consult any paper materials during the test. If another question that was asked was, what happens if you don't pass the test? Are you allowed to write it again take it again before the August 13th, which right now is the last administration. So you are, of course, allowed to take it again, but you have to be able to find a spot. So I found out, Leanne, that you don't even have to wait and find out if you have passed or failed. You can register for another session.
Wow.
But there aren't that many sessions available. So if you're going to do that, do it soon. And then people asked about how many times you'd be able to retake the test. So again, there's a question Rochelle is asking, can you use math manipulatives or even virtual manipulatives? And my understanding is that you're really not allowed to use anything outside of the test, and even a calculator, you're not allowed to use that excepting for the online calculator. And one of the suggestions we had on that video is that you should practice using the online calculator.
Okay.
Yeah.
That's very interesting. And I just think something to remember as we go forward as math teachers into our careers, that these ways that we're writing the MPT, we're doing this because it is something that we're being forced to do right now. But a lot of these strategies that we are experiencing from this perspective are really not really good things for us to be doing in our classrooms. I mean, even the timing, because I know that looking at the video that you shared, Lindy, talking about, thinking about 2.5 minutes per question in order to finish in the amount of time. All of the research shows us that being fast in your math doesn't make you a better mathematician, that we all learn and think and process at different rates, and that does not determine how good we are at math and stuff. In fact, some of the things that we're hearing here and experiencing from this perspective are the things that actually create that negative math mindset and the math stigma that so many of our students are experiencing. So while of course we can't do anything to change this, thankfully Lindy's here trying to help and support us to get through it. But I just think it's very telling, right, in terms of where we can go forward now as teachers, so that our students don't have to experience this, so that we can change that perception of math in our communities.
I just want to clarify, because there are a lot of questions about the paper. Are you allowed to take paper in? And so you are allowed to take paper and pen in. You have to show the invigilator that it's blank. And so you can use paper and pencil, but no calculators.
Okay.
Just the online calculator.
I have a quick question, if that's okay.
Go right ahead. And then we're going to get into the math, and then we'll take questions at the end. Okay,
Sure, just with the paper and pen. So we show them that, and then do we have to like pull up our laptops and like show them around the room and everything like that? Like, is that required of us, like the setting and everything like that? Do you know?
I really don't know. All I know is what somebody has already posted in the chat here is that there's like a special browser that you open,
Right.
and you can't use anything else. You can't have anything else open.
Candace, I can answer your question.
Go ahead.
So I have a few friends that have written it. You don't have to show your room. You just have to show your piece of paper that's blank, and you have to hold an ID up to the screen.
Okay.
Thank you, guys.
Not allowed any backgrounds. They said your background has to be clear, so you can add one in, like the options that go into the settings.
Right.
And you're on this browser thing, so you have to download it, and once you're on there, you can't access the internet without like shutting your computer, so you won't have access to anything like online.
And you also have to be on a Zoom call with the investigator and with the proctor.
Yeah, so they're watching you.
Yes, they're watching you. And I did find out today that you are allowed to go to the washroom, but you have to put it in the special chat. You say, I'd like to go to the washroom, and they have to say, yes, you can go now, and then you go. So I found out because that was another question that was asked. Okay, that's it about the test administration, because most of those things are we could maybe take some time if people want to stay at the end to ask any more questions. And I really appreciate everybody who knows some of that information sharing this with others. And now we'll go into the math content, since there were lots of those questions too.
Fantastic. Okay, so if it's okay with you guys, I'll pull up a couple of questions rooted in previous EQAO that relate and address those concepts that you guys have identified. I'll start with one of them, and I'm thinking that we really definitely need your feedback on this as to how in-depth we need to go. I'll show you the question. If we're not feeling comfortable, once you guys have a chance to try it and then we take it up, we can look in more depth at that particular idea. So let me just share my screen here. So basically, as we go through this, what I think is a good strategy for you is to consider the key concepts that you think that this question is trying to get to. Maybe then consider a plan about how you might attack the problem. And then if your plan, after we try to look at this together, doesn't really align with the direction that we really need to take, then kind of identify this as an area that you need a little bit more work in. So I've tried to kind of provide a variety of questions. So here's one question that I think that we could probably use to get started with. So my recommendation is that if you have a piece of paper or a pencil or a mini whiteboard, maybe take a few moments to see if you can establish a pathway to finding a solution to this. I'm going to give you a few moments to think about it before we talk about it together. I see some people were writing things down furiously, Lindy, so I'm going to give them another few moments. Because as we know from when we're working with our students, it's always better if we can try it first, and I don't want to do all the thinking for you.
And Leanne, this question that you're showing is not in Desmos, that's in your Delta math?
No, this is just something extra. So I'm leaving the Delta Math and the Desmos as takeaways that they could look at on their own. And I thought we would use these EQAO questions to actually discuss and maybe do a little bit of teaching if we feel that that need is there.
Okay, perfect. Thank you.
Okay, so let's read this together, because I know that since I'm not providing it as a document, you wouldn't necessarily have the Kurzweil if that's something that you are using to kind of have text to audio. So a sailboat is pictured below. Each sail has a height to length of base ratio of 3:2. If the height of the sail is 9 meters, which could be used to determine the base? So this was taken as a multiple choice question. I have purposefully taken off that point because I wanted us to go through it together and think through it from scratch. I didn't change the text because I wanted to prove to you this truly was an EQAO question, and this is the one that they should hopefully be pulling from. So any ideas what type of concept this deals with? And feel free just to unmute yourself and shout it out, guys, or the chat. Lots of people are using the chat. Yeah, go ahead.
Pythagorean theorem?
If I wanted to find the length of my side, that's right here where my cursor is, that would definitely be Pythagorean theorem. Okay, and actually we could practice that in a little bit if we want to. Any other ideas? We're getting some others, but I love the Pythagorean theorem because we recognized it was a right triangle. It is a matter of proportional reasoning. And I think that the takeaway from that is the fact that they gave us a ratio in here as well. This little 3:2 ratio indicates that they're telling us that it's not necessarily 3 meters to 2 meters, it's just a ratio of 3:2. So it could be 30:20. It could be 15:10. The fact that it's a ratio is going to give us an indicator and a little bit of a flag that I want to set that up as a ratio. So one of the things that I think are very handy for you is to actually outline exactly what is the height and what is the length, simply because that's part of what we're dealing with here. So we're noticing that we're given the height to the length, and I'm going to take our ratio and I'm going to actually write it as a fraction. And don't be afraid of fractions. They're just really ratios written without the little colon. So the first tricky little part about ratios is making sure that we set them up correctly. Once we do that, then we're pretty much good to go with our proportional reasoning. So we'll notice that the ratio of height to length is 3:2. So it's really, really important that I make sure if I choose to put my height first, that height will go where height should be in terms of what I've been given. So I chose to put height to length because that's the way it was written and I was lazy with that. If I had wanted to, I could have put length to height, but that would mean that I would have had to reverse my actual fraction that was describing that. Does that make sense, everybody? That whichever way I want to do it is okay, but I need to be consistent as I go through and do that. Okay, the way that we would move from here is that we're actually given a real measurement for this particular sailboat. So we're going to go ahead. If the height of a sail is 9 meters, basically we would want to find what the length would be. So this is where some students go off a little bit. Where should I put the number 9? Should I put it on the top or should I put it on the bottom? What do we think, guys?
Top.
Yeah.
On the top.
On the top. Okay. So it's got to go on the top because it represents the height. And we'll notice that we already had height on the top. Okay. So if this is too easy for us, you guys let me know. Okay. I'm just going to kind of gauge it as we're going to make sure we're good to go. And then of course, we want to know what the base, they're saying we could call that X. I'm going to put an X in there. So really what we've done is we've taken a very short word problem and we've created what we call a proportion, which is just basically two ratios that are set equal to one another. Do we have ideas about how to solve a proportion, how to find that unknown value of X?
So you have to cross multiply.
Okay.
Length times
So like 3x and then equals 18.
3x equals 18. Okay, so I'm hearing that. We're going to talk about a couple ways to do this. So basically, I'm hearing that you're cross multiplying. We're going to talk about what cross multiplication actually is in just a little bit. So you're telling me 3x equals 18, and then from there, what would you do?
Because you want to get s by itself, you have to divide it by 3 on both sides.
Okay.
And then your final answer would be 6.
Okay. So we notice the 3 is connected to the x by multiplication. So we want to undo that operation to get the x by itself. And I really like that you divide it by 3 because 3 divided by 3 is 1. So we're left with 1x equals 6. Awesome. That's a really good way to do that. Yeah.
I'm sorry, could I don't mean to interrupt you.
No, good.
Could we
Please.
just go back to how did you get the 3? Like, how did you arrive to understand that 3 goes underneath the 3x and underneath 18?
Okay. All right. So we're going to talk about solving equations right after this. But I'm going to address your question. I'm just jotting that down so that I kind of know a new direction that we're going to have. So basically, when I heard cross multiplication is really just a trick. And it's a shortcut to solving an equation. I think that it's probably good in just a couple minutes if we go back and actually look at solving equations so that we understand why this works. And that way we'll know when this sort of little trick could be used. For all intents and purposes, it's probably better to really just go back to the fundamentals for this. So we talked about basically what they did is they brought the x up on both sides. So let me go down here. I've got 3 over 2 equals 9 over x. When I heard about the multiplication, this cross multiplication that was discussed, what's really happening is that we're saying that I don't want to have 2 on this side of the equation. I want to undo this division by 2. And so to undo division, we always do the inverse operation, which I'm going to call multiplication. But an equation is like a teeter-totter. And whatever I do to one side of the equation, if I want to maintain the balance, I need to do the same thing on the other side of the equation. So we didn't want to have this 2 down here. So we multiplied by 2. That means we need to do the same thing on the other side. So over on our left side, notice we ended up with 2 times 3, which is 6, divided by 2, which is just giving us 3. And we ended up with 9 times 2 is 18 over x. Now, what the cross multiplication did is that they also noticed, took the x and moved it across. We still have an x in the denominator here that we really don't want to have there. So to undo the division that's here, we want to multiply. If we multiply the right side, we need to multiply the left side, and that's where we end up getting 3x equals 18, as your colleague had mentioned. To be quite honest, I don't know if you know, if you're reading between the lines, I'm not a huge fan of cross multiplication because I'm concerned that that's going to, if it works for you, that's awesome. But if you're having any difficulty at all, I think that us looking at solving equations together in just a minute will be helpful for you. So this whole idea of cross multiplication, you just kind of crisscross, but it only works in really specific scenarios. And then we end up getting an equation such as we have here. So 3 times a number equals 18. Sometimes we can solve these equations by inspection, meaning we can just kind of guess and check. So 3 times what number gives us 18? We know that 3 times 6 gives us 18. We can use that, but we could also use our rules for solving equation by undoing the connection between the 3 and the x. So there's multiplication there. So we could undo that multiplication by division. And that's where we're ending with x equals 6. Okay, I really kind of feel like I put a lot in there and we need to break that down a lot more. So I apologize for that if that seemed a little bit confusing. We kind of pulled a whole bunch of stuff into one thing.
Leanne, can you speak about other ways they could have gone into the answer?
Absolutely.
I think there are much easier ways to get to that answer, right?
There are. Because this is a ratio and we're just looking at equivalent fractions, really, if I know that 3/2 is equal to 9/x, I can think about what could I do with the 3 to get to the 9. So we're always looking for multiplicative relationships when we're comparing ratios. So if I think about the 3, I can consider if I multiply by 3, I can get to 9. That being the case, if I want to create another fraction, I could multiply my denominator by 3, and you can see that we can get to 6 much more efficiently. So when we're looking at ratios, there's many different ways to do it. The idea of the cross multiplication that kind of evolved into that big complicated, what kind of felt like a mess, it works, but lots of times there's better ways. So we can look at the relationship between two ratios. We can even look at the relationship within a ratio. Lindy, I'm thinking, can we just try a couple of these easy ones for just a minute? Because I feel like this got complicated. My concern is that teachers might start to think that this is really hard.
Sure.
Is that okay?
Absolutely.
All right, so let me just pull this up. I've just pulled together some stuff, ratios and proportions, and lots of times what we like to do is just kind of create cards. I don't know how many of you are familiar with a thinking classroom, which Peter Liljedel's research, something to look into as you go into your own math classrooms, if you are going to be a math teacher in some capacity. Basically just trying a whole bunch of questions, working at whiteboards. These are some that we've used in the classroom to practice this concept. So let's just try a couple together, because I really want to convince you that you can do this and it's not as complicated as it was. I wanted to honor the fact that that was an approach that was offered. However, we can look at it in other ways too. So let's take a look at the first one here. We have a proportion because we have a ratio on this side and a ratio on that side. What I want to do with it, I'll do the first one with you and then I'm going to let you guys try. I want to write it as a fraction. I think that's the easiest way to look at it because we're a little bit more adept at working with those. So if I've got the ratio 2 to 5, I'm going to write it as a fraction of 2/5. If I choose to put the first term as the numerator and the second term as the denominator, I need to be consistent with that. So I need to write the second ratio in the same way. So here's an example. We could use the cross multiplication, but we're not going to do that right now. Let's see if we can find an easier way. If I want to find an equivalent fraction, I can look at the relationship between our two ratios. And I just ask myself, what would I do with 2 to get 8? So what's our idea? What would we get 2 to get 8?
Multiply it by 4.
Yep. And whatever we do to the numerator, we're going to do to the denominator as well. So obviously, what's that going to make n equal to for us?
20.
Yeah, awesome. So there's lots of different ways we can do it. You could also look at, trying to find relationships within, but I think the way that we did it here was the easiest way to handle this problem. Okay, do you guys want to try the second one? I'm going to give you 30 seconds.
Leanne, I'm just going to comment that each question on the test has such a little bit of time allocated to it. So I think that even though there are always multiple ways to come to an answer in math, finding the quickest and easiest is the best way for this test. Because if you free up your time, you're going to have more time on some of the questions that are harder for you. So I think finding the simplest and quickest way to come up with the correct answer, of course. And of course, you could check it in different ways, but I think this is really the approach.
Okay, sounds good. I agree. All right, so we're seeing lots of good stuff written down here. We're seeing it written as a proportion, so 4/15. I'm just looking at the chat, 8/n. I'm seeing again, people are showing that they're multiplying by 2, and so they're getting n equals 30. Awesome. Okay, so the great part about that is that many of your ratios will be like this. There will be some where it won't be integral values, meaning that there might be decimals. And that's, I think, where that cross multiplication or the solving equation approach actually comes in handy. I think probably what's best is that if the need arises, we talk about how to solve an equation rather than go in deeper in this way here. Do you guys want to try another couple, or are we fine with this? Can we move? Would you like to move on and look at other ideas? Okay, so yeah, sounds good. All right, I have some other ones left ready to go. Do we want to look at equations first, though? You guys tell me.
Sure. Equations
Okay.
is good.
Equations is good. Okay, so let's take a look here. All right, sorry guys, I'm just grabbing it here, pulling it up. Just something I want to mention really, really briefly before we go forward here is the idea behind how you're solving the equations, and then we'll just try to practice a couple together.
Sorry, Leanne, before you move forward, I was just looking at that number 3 of the last ratio question there, and it was written where it was n to the n ratio 5 equals 12/20. Even though that n is still in that top left value, am I still doing multiplication, or do I have to switch operations because I'm solving the other side of the problem? Does that make sense?
Let me look at it back again just to make sure I'm understanding where we're going. So you're talking about number two? Sorry.
Go down.
No, number 3. I saw number 3, so I wrote it down.
Perfect.
And
perfect.
then I was like, oh wait, hold on, it's in a different place. Do I have to do something different?
Okay, what was your question again? Can you say it again, please?
Yeah, so I was just wondering, so when I wrote these down as fractions, I have n/5 equals 12/20.
Yep, you got it.
So and then I would be do I still multiply, or do I now have to divide?
Okay, so what's your thinking? Because obviously you're not feeling comfortable multiplying.
Well, I am feeling comfortable multiplying, but I just wanted to make sure that that's what I would be doing.
Okay.
I'm making sure that I'm not confusing myself because it looks slightly different.
So in this situation, since we have our n on the left side and it seems like the smaller denominator, keep in mind we can flip these too, right? If that helps you, what's a left side and a right side? As long as I take whatever's on either side and completely swap it, I can do that. So if I wanted to, I could write that as 12/20 equals n/5, and then we could look.
I'd be multiplying them by 4, right?
Yes, well, you would be, so I'm looking here. If I'm going to the left, I am multiplying the 5 by 4. Does that make sense?
Yes,
so whatever is my n, I'm multiplying that by 4. So in our heads, what's the number that we would multiply by 4 in order to give us 12?
3.
3, awesome. So that being the case, when you said, is this division? Yeah, it's division and multiplication. They're inverse operations. So depending on how you like to think about it, you can just think, what number should I multiply by 4 to get 12? But if I'm starting at something that's a larger number, notice that if I move from the 5 to the 20, I'm multiplying by 4. But if I want to go in the opposite direction, that actually goes the other way. It's division by 4. Does that make sense?
Yeah, that's what I was thinking in my head, but I just wanted to make sure that if that's what I put in my head of how to solve it, it was the correct way.
Yeah, it absolutely was. Now, a really good trick when you guys are finished with these, if I wanted to, if I have our answer, so we've got the answer 12/20 or the question, and we had 3/5 as our answer. If I were to take my calculator and go 3 divided by 5, that's going to give me 0.6 as my answer. If I was going to take the 12/20, it's still going to give me 0.6. So I can always check before I move on to make sure that I've done it correctly. That's a little check. Is that okay?
Yes, thank you.
You're welcome. Okay, I'm just trying to keep an eye on the chat. Oh, solving equations, that would be perfect. Okay, so let's go ahead and take a look at those equations, and we'll look at that very quickly here. So let's talk about, we'll start with some super easy ones, okay, you guys? And really kind of the foundations behind how you would solve an equation. I say that not because I don't want to waste anybody's time, but my concern is that you guys have a lot to kind of manage. If you understand why you're doing stuff, this stuff actually becomes pretty straightforward and easy. If you're trying to memorize how to do stuff, it just becomes, at least for me, really stressful. So with equations, basically what we're doing is trying to get the letter, the variable by itself. And it's like a knot that we're trying to untie. So we have connections between our variables or letters and other numbers. And we want to undo those connections. So if I've got something here, my variable, my letter X is connected by addition. So to undo that connection, to undo that knot, I would subtract. If I have a connection that is via multiplication, I would undo that by dividing. Does that make sense to everybody? And vice versa. So those are always going to be the different operations that you are going to take a look at. So for instance, let's just look at the first one since it's right here, super easy to access. Whoops. I know these are easy ones, but we can get some harder ones in just a minute. Let's say I have X plus 5, and I know we can solve this by inspection, so just bear with me for 30 seconds so that you can understand the why. If I want to undo the plus 5, obviously I'm going to subtract 5. We talked a little bit earlier about an equation being like a teeter-totter, and what I do to one side, I've actually got to do to the other. So if I want to get the X by itself and I want to subtract 5 from the left side to make that become nothing, to make that just be an X, then I need to do the same thing to the other side. So notice that by doing that, we actually had the 5 subtract 5. We're just left with the X and we get our answer, which I know you could have known just by looking at it and saying by inspection, well, I know that 7 plus 5 gives me 12. Similarly, when we have something like 3y equals 27, since the connection is multiplication, I want to undo the multiplication. Ideas about what operation would undo multiplication?
You would divide the 3.
Excellent, excellent. Because we don't want to have 3y, we want to have y or 1y. If I divide the left side by 3 to undo that connection, I need to divide the right side by 3 too. And that's where we're going to get our y, because our 3 divided by 3 is going to give us 1, and we're going to get y equals 9. Okay, so lots of connections. Let's take a look at the third one here. Okay, notice that this connection, there's a couple of connections instead. So this is probably kind of the hardest you're going to get because there's going to be multiple connections. And how I always think about it is that we're trying to get to the variable. It's like we're trying to undo the knot. And I think about if I have a knot in my necklace, I always start with the loosest part of the knot first, undo that until I get to the really tight knot. So we have a number of connections here. Notice we have a connection that's further away from the letter. We have a subtraction connection, and we have a multiplication connection that's really tight or really close to that variable. I want to undo the loosest connection first. So I notice that I'm subtracting 7. That's kind of the furthest away from my variable. How would I undo that subtraction 7 connection?
Add 7.
Add 7. Awesome. Hillary, do you have a question too?
Oh, no, I was going to answer.
Oh, perfect. Okay, awesome, awesome. So we're going to add 7 to both sides. Awesome. Notice that the subtract 7 and the plus 7, That made that go away, which was our purpose. We're getting closer and closer to getting that variable by itself. We're left with a 2n over there. Obviously 9 and 7 is going to give us our 16. And now we need to find our n. So one last connection. How do we undo that 2 connection?
You basically do 16 divided by 7, and then 2n divided by 2.
Divided by 2. Awesome.
sorry.
Awesome. Awesome. So we've got the 2. Yeah, I love it. Because they're connected by multiplication, to undo the multiplication, we'll divide, and we'll divide by 2. And that's why we'll get our n equals 8. Sorry, guys, I wasn't wanting to, I had actually not planned to put it all in here like this, but I know time is of the essence. So I wanted to do that quickly, just as a little.
It's awesome, Leanne. You're doing great.
Oh, it feels a little scattered. I apologize, you guys. Okay, so it's the, the left side, right side. Now, for those of you who are wondering why we're undoing this, in case it helps you, can I move my screen down, or do people need a little bit more time?
Keep going, Leanne. I think you're
okay. All right.
You.
All right. Perfect. For the
that big one, can we do the big one that has variables on both sides of the equals?
Yes.
Thank you.
Absolutely. Absolutely. Can I show you something and then we'll do it? I'm kind of building up to it. Is that okay? I just want to show you why we're going to do what we're going to do there. So one of the ways that for you guys visualizing this is like a hanger. We talked about a teeter-totter. Another way that's really handy, this equation, say x plus 3 equals 7. I can look at balancing a hanger. So notice I have an x here, a plus 3. Really, if I want to just get the x by itself, it's like I'm cutting off part of that hanger. If I'm cutting off 3 from here, I have to cut off 3 from there in order to make it make sense to us. Okay, so that's another visualization that might help you. And I actually find that that becomes very handy for situations like we have here. So I just want to show you a hanger representation of that one, because that's the one thing that people tend to have a little bit of difficulty with, is this one that you're asking about right here. So let me just show you a hanger representation of something very similar to that. And I think it will make a lot of sense to you after we do that. So I'm just going to pop over here. Sorry, guys, I'm kind of pulling things together. So here's a hanger representation. And I know that, mathematicians often say, oh, we got to use algebra. To be quite honest, it shocks me a little, Lindy, that they're not allowed to use manipulatives for this. Because manipulatives are actually a very high form of learning. And for us to be able to visualize things differently is okay. So when you guys are solving your equations, if you need to draw a picture, that does not make you less of a mathematician to draw a picture.
Leanne,
so,
if you want to be shocked, stick around. There's so much about this test which is shocking. So, yeah.
Incredible, isn't it, Lindy? Okay, so let's do this one together. This is very much like the one that you just asked about a moment ago, except I wanted to show you the hanger version first so you could understand why we're doing what we're doing. So the fact that these are balanced makes it equal. Okay, so I'm going to put my equal sign down there. On the left of my equation, can you guys see I have an X tile and a +9? So you might see that represented like that. You're probably not going to see the hanger model, but really that's what the hanger model is that's what the equation is illustrating. Over on the right side, any guesses about what this right side might be represented by algebraically? Any guesses?
4 times 3x.
Okay, I love it. We've got the 3x, okay, because we've got 3 of the x's, and we've got a 4 added onto it. Okay, if you didn't get that, don't worry about it. They're not going to give you a picture like this and ask you to interpret it. At least I don't think so, but they are probably going to ask you to solve it from here. So what I want us to see is that we said that we wanted to get a variable by itself. The problem with this one compared to the others is that we've got variables or letters on both sides. I don't want that to happen. So a really good way forward is for me to cut off one of the X's, and I would maybe cut off that X that's there. So if I cut that X off my hanger, it's going to go topsy-turvy, right? So that's going to upset my balance. So if I'm going to cut the X off of one side, does it make sense I need to cut the X off the other side as well? So that's just like saying, okay, I don't like the fact I've got X's on both sides. I'm actually going to cut off or subtract X from that side. If I subtract X from that side, I'm going to need to subtract it from the other side too, so that I maintain that balance. And by doing that, I notice that my X's are going away. So I'm going to be left with just 9. On the right side, I have 3X subtract X, which is 2X. And of course, we had our plus 4. So we've basically taken that thing that looked kind of ugly and made it into something that you're already very proficient at solving. Now, I want to mention, because we talked earlier about tricks and that sort of thing. There are people, maybe the way you learned this is that you notice that, oh, this is X that's added here. When I bring it across the equal sign, I change the operation. I'm not sure if other people saw that or have experienced that. But that is another possibility that some people might go with. The reason why I'm not doing it that way is that it actually fosters some misconceptions later on, and that this way that we're talking about it right now is more of a foolproof way, okay, rather than kind of the tricks that we're not sure when we apply them. All right, from here, where would we go, you guys? If I wanted to now try to get the X by itself, what would be our next step towards isolating the X?
-4 on both sides.
Awesome. So we're going to -4, -4. When I do that, we know that the 4 and the -4 go away. That was the whole purpose. So we're going to get 2X equals 5. And then what's our last step to try to isolate the X or get it by itself?
You divide the 5 by 2 and but the 2 by 2.
Yep, awesome. So we're left with X equals 5/2 or 2.5. Keep in mind, if it's got it like that, writing it the other way means the same thing. Okay.
And I have a question.
Yeah.
Am I able to bring the 4 over to the 9 side and keep the 2 on its own?
Yes, that's the same sort of idea. So we were mentioning, I'm going to put that in another color. What you're doing is exactly the same thing. So when you learned it years ago, you may have been told to go ahead and take and change it to the opposite operation on the other side, right? Is that what I'm hearing?
Yeah, you're right.
Yeah, so the addition of the 4, you think about it as subtracting on the other side.
Yep.
And you're going to get the same answer. Now, the way that that causes problems later on, let me just share, because that's an awesome way to do it. But let's say I have something like this, -2X equals 4. Let's think about how we would solve that equation. What would we do? Okay, I know this is kind of one out in left field, but I just want to make sure that with your idea about bringing stuff across, that you understand where you need to be careful there.
You'd have to bring 2 over to the 4.
Okay. See, the question here is, because it's a negative, sometimes we think that we would add it, right? That we would bring it over and it would become a positive. But in essence, the operation, the connection between the -2 and the X is actually multiplication. So it has nothing to do with the sign. So to undo -2 times the X, we actually have to divide. Okay, so we would divide by -2 so that we would get a 1 here. If we divide the left side by -2, we need to divide the right side by -2, and we would get X equals -2 as our answer. Do you guys see where I'm going with that? That you have to be really careful with that trick about bringing it over. Is that okay?
Yep.
Okay.
Or can I just ask a question?
Yeah.
So if you're bringing the number, like the number over, would you just, like, if it's a number on its own and there's no variable, you could bring it over? But if there is a variable, you wouldn't bring it because it's negative 2x, you don't bring the 2 over. That's why you have to divide it.
Yeah, you're always undoing the connection. So that idea with the, bringing it over and changing the operation works well. Like if you think about this one here, the negative 2x equals 4. In your train of thinking, you're bringing it over, you're dividing. So it was multiplied, it was multiplied over here, you brought it over and you divide it by the negative 2. Okay, that's what your train of thinking does. What you have to be really careful of is that you don't change the sign. That's where these little tricks become a little bit treacherous.
Yeah, there was some confusion caused around the hanger because some people thought they couldn't understand why it wasn't 9x as opposed to 9 plus x.
Perfect. Okay.
And that confusion was compounded because on the other side you had 3 x's, which became 3x.
Right.
Just if you could just, I know people are not going to be asked to interpret the drawings in the test, but if you could just help people not feel confused by that, that would be awesome.
Absolutely. So if I wanted to write 9x over on this side, I would have to have 9 of the little
x's.
And I apologize, guys, because you know what, normally we would have tiles and we would work through this stuff as kind of preliminary things. We're popping right in the middle. But that's how that would be different, is that if I wanted to have 9 x's, then I would need to have actually 9 of those x's. The reason why these models, even though it's not on it, I wanted to show it to you, was simply because it allows us to see what we really mean by 3 of x. We mean 3 of something, whatever that something is. In this case, the something is a green triangle. So since I've got 3 of those somethings, that's why we're writing it as 3x. Over here on the left side of the hanger, I only had 1 of those triangles. So that was actually a 1x. Now, mathematicians, sometimes they're a little bit lazy. Instead of saying 1x, they just say x. So if ever you see something and it doesn't have a number in front of it, it's implied to be a 1.
Thanks, Leanne. Can you go back and do the one that was the original question? Awesome.
Absolutely. Yep, for sure. Let's grab up to that. Okay, let's put this down here so it's a little bit easier to see. So 5, whoops, I guess it would help if you're on the same page as me, right, guys?
Sorry, I have a quick question.
Uh-huh.
Is the diagram you showed us, is that called a manipulative? Is that what it is? Like, what is a manipulative when they talk about it in the curriculum?
Manipulative is actually something that you can touch with your hands and manipulate. And what we would do in the classroom is that I would give students algebra tiles. So they would be tiles and we would just randomly call one X and one Y, and they would be different tiles. So we would be able to actually take the algebra, all of the stuff that looks so intimidating, and actually make it into blocks, really. That's what manipulatives are.
Okay.
What I showed you was more of a diagrammatic approach to allow us to visualize what was really happening. One of the challenges with math learning is that we have been conditioned over many, many years to go directly to this algebra, which we call the symbolic, when in fact, when we're learning math, we really should go from concrete, like hands-on you're talking about, to a diagram, and then to the symbolic. So this should kind of be the last step. Okay.
Thanks. Okay.
You're welcome.
Is that more like discovery math? I'm just curious because like when I was in school, we just had numbers and that was it. So
Right.
is that different than discovery math?
Well, I don't know what discovery math is.
Okay.
It's something I read about in the paper that I think the government put a name on. I think what they mean by that is that students aren't being made to memorize facts and tricks, and they're allowed a little bit more creativity. So I think that's what discovery math means, is that we're, hopefully going forward, going to allow students to be more creative in their thinking. I think that's what it means.
Thank you. Yeah.
You're welcome.
Thanks.
You're welcome. Okay, so as Lindy mentioned, this is a great one for us to try here. Again, we've got variables on both sides of the equation. This is where this is the hassle. We've got choices, right, guys? I could try to get it so I don't have variables on the left, or I could try to do it so I don't have variables on the left, or that I don't have them on the right. So there's probably like 10 ways to solve this question. I would think it's easier for the purposes of efficiency. Let's make it so that we only have variables on the left, okay? So what do I need to do to the right side so that I don't have variables there anymore?
Divide by 2x?
Almost. We're not quite ready. Since we're not quite ready to divide because we don't have all the x's together. But I noticed that I've got 2x subtract 18, and it's almost
Add 18.
like I could add 18. Yes, we could do that. Let's first continue with what we started with. We're gonna get to the 18 in just a second. We want to make it so that we don't have any x's here. Right now, we've got positive 2x here. We're going to subtract 2x. And I apologize. Normally, I would go with whatever you're saying, but I really do want us to make sure that we're going to do this as efficiently as possible, okay? So we're going to subtract 2x from both sides. And the purpose for that is we have a 2x subtract 2x. We're kind of getting rid of that 2x. Once we do that, can we see that we're left with minus 18 on the right side? Is that okay with everybody? And if we've got minus 18, let's look at what we're left with on the left side now. We had to subtract the 2x because we didn't want to have x's on both sides. So we had to do that on the left side too. How many x's left over here on the left side then?
3.
Yep. Awesome. So we've got 3x, and we still had a 6 there that we had to deal with. And now we've created an equation that we can deal with in other ways. Okay, what would be our next step now if we wanted to get our 3x by itself?
So you subtract 6 on both sides.
Awesome. Okay, we know that 6 subtract 6 is going to give us 0. That was the whole purpose of doing that. We're left with 3x on that left side, and then negative 18 subtract 6. What's that? Negative 24. And then what would our last step be?
Divide 3 on both sides.
Perfect. And we're left with x equals negative 8. I just want to say, when you were talking about adding 18 on both sides, that will work as well. It just will be a few steps longer. It really hurts my math heart to not go with that, okay, and not value that, because I do value it, and it's an absolutely valid approach to take. It just would have taken us longer, and I didn't want people to infer that we had to do it that way. Is that okay?
Perfect, Leanne.
Okay. All right, so you guys tell me what's next. Do we feel good? Because I know some people said they were writing the test tomorrow and they really wanted to do equations. So I think that was important. And I don't know if you'll have a calculator for this type of question or not.
There are 2 sections of the math content, Leanne, and some of them have calculator and some of them don't. And it's difficult for us to know what kinds of questions you'd be asked in each place. So it's hard to say if they would give you a calculator. In general, the questions that they're asking without the calculator are not, they're just testing your addition and your subtraction and your multiplication. That's more what they're doing. And you are, yes, limited to only use the digital calculator. Because section 1 is number sense. So there you go. As I say, they're testing your ability to add, subtract, multiply, and divide.
Okay, we had already, do we want to do Pythagorean theorem? I'm also seeing linear. I heard Pythagorean a little while ago, but we could do linear as well. Which direction would you guys like to go with that?
Linear, please.
Let's do linear, yeah.
Okay.
Pythagorean, please.
All right. Okay. Let's do a little bit of linear and then we'll do Pythagorean theorem. Is that okay? Yes, I'm just looking at what
we've got 21 minutes.
Okay, so we'll have to do linear very quickly. And linear, I mean, it's amazing because everything actually connects. which is hopefully, you know, what we get to see as we learn. I learned so much when I started teaching, and I was like, I didn't know that connected to that and that and that and that. So the linear does connect to the ratios, which connects to the unit rate, which connects to slope, which connects to everything. I'm scrolling through here to get to where we need to be. This is an example of a linear one. Let me just find out if, because since we have 21 minutes, something that is going to help you with that. There was also other things here. I'm just trying to choose the best one here that will be good for us. So when we're talking about linear, you guys are talking about, are you referring to, you want to be able to interpret, find the initial value of linear relations and maybe the rate of change? Is that the part that you would like to look at? Yes, okay, all right. So let's take a look at this example. I'm going to read it quickly. I know you're all capable of reading, but in the effort to try to move quickly. Information about the linear relationship between the total cost of skiing, C in dollars, and time T in hours at 3 different ski resorts is shown below. Determine the initial value for each relationship. I think that in addition to the initial value, let's also find the rate of change, because I think you'll likely be asked that on your assessment. So do you guys know what it means by initial value? Does that sound familiar to anybody?
No, I have
Okay.
no idea what you're talking about.
Okay, no problem, no problem. And you know what? This is like EQAO speak. When I first started teaching, I'm like, what? I have like how many years of math, and what the heck is an initial value? Honestly, I felt the same way. So initial is like what it sounds for us. When I say initially, I thought this, then I changed. So it really just means at the beginning. So when we're talking about the initial value of a linear relationship, we're talking about where it intersects the y-axis. So basically the y-intercept, that's the same thing as initial value. So it's, don't be put off by the fact that they're calling it initial value. It just means the y-intercept or the vertical intercept. When we're looking at particular situations, it also might mean the base cost. For instance, if we were to take a look at the third situation here, I noticed that my line starts at 15 and then it goes up to the right. So how I would infer, what I would infer from this is that, let's say I am trying to go skiing and I haven't been there at all. So I just kind of went in and paid, and I'm still paying 15 bucks plus notice that it's going up with every hour that I'm actually skiing. So my initial value for this particular one would be $15. What that translates into is just my base cost. How much is it going to cost for my ticket before I actually go on the ski hill? So when we're looking at initial value, it's actually the amount it costs for 0 hours. Now, for this situation, we could say that the initial value was $15. I could also use this graph to figure out how much the hourly cost was. Okay, and this is where it gets a little bit challenging. Any ideas what mathematical concept can help us to figure out the hourly cost that is here?
Slope.
Oh, awesome. I'm impressed, actually.
Really?
So
Is it right? Okay.
Yeah, you're right. That's awesome. So is slope familiar, or should we talk a little bit about what the heck slope is?
Yes, please.
Okay. All right. So slope is basically the steepness of a line. And we take the rise of the line, meaning how much is going up, and we divide it by the run of the line. So it's just like a cost per hour. I think this is your formal mathematical definition, but when you're looking at this, I notice here, let's say I'm starting at 15 right there. Okay, right at my initial value of 15. I notice in 1 hour, my graph is showing me that it's costing $20. So for each hour, since I started having to pay $15 and after 1 hour, I had to pay $20, I noticed that it rose, or the rise was $5 for every hour of run. So it was like $5 per hour. So I noticed some people asked about unit rate. It's just another way to look at slope. So they're getting all of these different ideas. Sometimes they call them different names, but it really just means the same thing. Okay, so in this situation, our initial value, you asked about lines, initial value is where it starts, and our hourly rate, that's like our slope. So one of the other things you might be asked to do in this situation is actually create a rule that would describe exactly what the cost is going to be. So if I have cost here, I know it would be $15 plus $5 for every hour. So $5 times the amount of time that I'm actually going to go skiing for. Does that make sense to people? Oh, look at you guys. Okay, people are asking, would this be considered partial variation? For those of you who know what that is, yes, this is partial variation. Don't be put off by that word. I'm not sure that that will be on. When we talk about partial variation, this is another word that until I taught grade 9 math, I didn't know what it was, okay? So partial variation just means that it doesn't start here at 0, 0, that there is some sort of base cost that I have to consider. So it's like $8 plus so much per hour. If I'm taking a taxi, there might be a flat fee of $5 plus so much per kilometer. Anytime there's a flat fee, it's this partial variation idea, okay? Which means that it has an initial value that's not 0. Now, if we take a look at the second one here, I've got at mountain ski, my equation is C equals 8T. What do you notice is different in this equation as opposed to the one that we just created here?
There's no base cost.
There's no base cost. Excellent. So if I wanted to, since the base cost, there's no base cost, that's another way of saying the base cost is 0, right, guys? So what would the initial value be for this relationship?
0.
It would be 0, exactly. And in this case, this 8T would mean that it was costing $8 an hour to ski. So they weren't going to charge me coming in the door, but notice they charged me a little bit more of an hourly rate that I had to pay, but they didn't charge me a base fee. So another way to say this unit rate is the same thing as the slope. When you hear that, that's all it means. It means like the hourly rate that someone is paying. Okay, all fancy words for pretty simple ideas. This last one's kind of hard. I'm going to warn you, okay? Because we're only being given a table of values. So we need to find the initial value. I want you to look over here for the other ones. We said that the initial value is how much it cost at 0 hours, but there was no 0 hours in my table. So we would need to be able to use a little bit of deductive reasoning to figure out what that initial value would be. Any ideas? Any guesses before we move on? Okay, I'm hearing 0. Why are we thinking 0?
Because it's going up by 10 each time.
Awesome. It's going up by 10 each time. So we notice that if we just want to extend the pattern, clearly, if I go backwards, I would have to subtract 10. And so our initial value would be 0 there as well. Now, what would the hourly rate be for this ski slope hill that we looked at?
$10.
Yeah. So let's look at that one. Could we make an equation for that one?
C equals 10T.
Yeah, awesome. Now notice since that the initial value was 0, since there wasn't a base fee, that's why we don't have anything added on to the end of that. Okay, what other questions do you have about this one? Because I know we said we would do Pythagorean in just a minute too. Okay, I'm going to pop over. Is it okay if I get away from this for just a minute?
I think you're good.
Okay, fantastic. Let me go to the measurement here. And I want to look at Pythagorean theorem. Now, when you guys have thought about Pythagorean theorem, I'm sure you thought a squared, c squared equals a squared plus b squared. Do people think of that? Is that accurate? Okay,
Yeah.
but the problem is that sometimes we don't know what the heck is c squared, and what if we change the letters on the triangle? So I want to show you what Pythagoras really said. Okay. First of all, Pythagorean theorem only works for right triangles, only ones with a 90-degree angle. And the first thing you're always going to have to do is make sure you know what's what we call the hypotenuse. Okay, and it's always the longest side directly across from the right angle. Okay, so I'm going to show you what Pythagoras said, and then we'll just try one or two little questions. Okay, because I think that us looking at it this way is going to be very handy for you. Okay, so what Pythagoras actually said is that here's my right triangle right in the middle. The area on the hypotenuse is equal to the two areas added together. If this is something that's feeling like it's blowing your mind, there is a Desmos activity that kind of takes you through this step by step, okay? And will allow you to try it and to actually practice and enter your answers and check them for correctness, okay? So let's take a look at this and let's find the missing side. So this is one we can try together now that we've kind of revisited what we actually mean by Pythagorean theorem. Be careful, as we mentioned, it's only applying to a right triangle. If it's not showing that it's right, then you cannot use this theorem. Okay, I know that on previous EQAO tests, sometimes, I think it's a little nasty, but sometimes they do that. So what we're going to notice here, a good strategy for you is always to highlight the hypotenuse so you know which one it is, because we know that that's got to be the biggest area. So then I'm going to draw in some other areas here, and I'm going to find the areas on those other sides. Okay, so I know this is a square. How will I find the area on the square that's right here? I know some people are already through this. How will I find the area here? Are we okay that that's a square? So I could go 10 times 10, which is going to give us 100. Okay. Our area on our square over here is going to be 7 times 7, which is going to give us 49. And if I want my big area on my hypotenuse, I know that that would be the same as length times width, or c times c is c squared. And we said that we would add those two little areas together. So I would get c squared equals 149. From here, notice the question didn't ask us to find the area. The question actually asked us to find that side length. Thinking back to solving equations, how do we undo a square? What's the button on our calculator that we could do? I see square roots. So we would take the square root of both sides, and we would get our answer c equals, and then whatever is that, 12 point something? Is it 12.2? I'm doing it in my head.
12.20.
Okay. Okay, so I'll say approximately 12.2 approximately. Okay. Now you may have seen this as c squared equals a squared plus b squared. Notice that's the same thing that we are doing here. The reason I am showing you it this other way is because when they give you something that's a little bit weird, this method that I'm writing down really quickly here that you might have learned in elementary school sometimes causes people trouble. Okay, so let me show you one last one so you can maybe get the idea of why we're doing it the way that I just showed you here.
Sorry, Leanne, I have one question.
Yeah.
Interrupt. This may be a really silly question too, but
never silly.
Are they always squares? Like, do we know for sure that they're always squares whenever we expand the triangle?
Yes, I'm always going to use squares. It could actually be any shape as long as we were consistent with the shape. It's the area on the hypotenuse is always equal to the sum of the areas on the other two sides. I don't think you're going to get a situation where you need to use something other than squares.
Okay, thank you.
You're welcome. Squares is the simplest way to do it. Okay, let's try this one last one because I think that this is where if we're going to get mixed up, we're going to get mixed up.
Questions, is there a square root on the calculator on the test? I hope so.
I hope so. I can't imagine they would want you to do that in your head, right?
There's not. There's not. It's been confirmed. It's
Okay.
just a very basic calculator.
Okay.
Maybe then they don't ask a hard square root, like 149. I forget what you had, 149. That's hard to do the square root of. But maybe what they do is
there's
they
a square root button on the MPT calculator.
Okay.
Yeah, there's a square root. There's just
you have to hit the number and then the square root button on the actual calculator that they have.
Yeah, there's just no way to put in the exponents. You have to do it manually, but there is a square root.
Okay, good.
Okay, fantastic. Okay, so let's highlight our hypotenuse. Which side is the hypotenuse?
25 centimeters.
25
Awesome. Awesome. Okay, and what do you notice is different in this question as opposed to the previous one? What was different here?
You're given the hypotenuse and it's kind of flipped around.
Exactly. So this is where the area model actually comes in handy to make sense of things. I'm still going to try to find the areas on the sides that I'm given. So the area on the hypotenuse is 25 times 25, which is, I think, 625. But you could use the calculator for that probably. We've got 9 times 9, which is 81. And notice the side, like you guys already noticed, the side that we don't know is the one that is not the hypotenuse. So here's what's going to happen. Pythagoras told us that the two smaller areas add to make the bigger one. But this time we've got the bigger one and one of the smaller ones. So what would we do with the big area and one of the smaller ones to get the area that we need to find?
Subtract?
Yes, exactly what we're going to do. So we'd go 625 minus 81, and then you would take your calculator and work from there. Okay, so that's why you're doing what you're doing. Now, if you you had the c squared, because the challenge, Lindy, is that lots of times people say, okay, they know that a squared plus b squared equals c squared, but then there's another formula that's a subtraction one, and I don't know when to use the subtraction, and I don't know when to use the one that adds. And I think that causes a lot of confusion. That's why I think it's easier just to draw the picture and you can see it. As long as you know what you have, and you got the big one and one of the little ones, then I need to subtract to get the other one.
Do you want to solve it then for them, Leanne? I did it on my calculator, 625 minus 81.
Yeah.
My calculator gives me 544.
Okay, and then what's from there? Well, square root. And what are we getting for square root of 544, Lindy?
I don't have a square root on this calculator, so okay.
I got approximately
23.32.
Thank you, 23.32 centimeters. Okay, awesome.
Yay.
I hope that helps you guys. I hope it wasn't confusing. I hope I didn't add to confusion by showing you the diagrammatic approach. I do think it's going to serve you best in the long run.